Autonomous driving has seen explosive growth during the 2010s. The field's aim of automating land-based transportation could revolutionize travel and transportation. With successes from companies such as Tesla and Waymo, autonomous driving might go from fiction to reality sooner rather than later. ADI is an autonomous driving platform developed in the Royal Institute of Technology in Stockholm, also known as KTH. During 2020, a team of master's students from the Mechatronics track got an opportunity to contribute to its development.
ADI is a software built to both simulate autonomous driving experience to be able to test various driving scenarios in the computer, as well as implement the software in real life together with an actual car. Our work on this platform has been to integrate the platform with a research vehicle to get this research vehicle to drive autonomously on campus. To do so, we had to look into two major concepts. The first one is localization. The car needs to know where it is relative to its environment in order to know where it should drive. To do so, a number of systems are in use, such as GPS, odometry and NDT matching. The main focus here is NDT matching, or normal distribution transform matching, which is a type of localization algorithm. The algorithm takes thousands of points in space that it sees from a mounted 3D sensor on the car and tries to match these points with an already created point cloud map of the world. The 3D sensor that we use here is a LiDAR, which is a sensor that scans the environment by emitting laser beams and creates points in space when it collides with an object. Compared to GPS, the NDT matching algorithm can get a much higher precision of localization. The second concept is planning. So in order to drive from point A to point B, we need to know the route between these 2 points. Here we can create a vector map of available routes based on our point cloud map that the ADI platform can use to compute the best route.
The mapping was done in a Renault Twizy vehicle using a custom-built sensor rig consisting of a LiDAR, GPS, gyroscope and accelerometer. This is a representation of the LiDAR scans, called a point cloud map. Each point represents a place where the LiDAR laser was reflected back into the LiDAR. The LiDAR measures the time it took for the laser to be reflected, which allows us to calculate the distance to the reflecting surface. These points can be used to generate a surface which approximates the real world, allowing a digital representation of KTH campus to be used in simulations. Before testing the RCV in the real world, we needed to make sure it can navigate in a simulated environment. During this project, we used pre-scan to simulate these environments and verify that the vehicle is ready for physical testing. By conducting a hardware-in-the-loop test during the simulation, we could see that the physical vehicle behaved in the same way as the simulated one. Here is the entire process visualized, with the hardware-in-the-loop test on the left, the simulated world in the middle, and a visualization of what the vehicle sees to the right. The outdoor testing was successfully completed in December 2020. The research vehicle drove autonomously using the ADI platform and even demonstrated an ability to go around corners.